não encontrei ninguém que tenha a beleza dela. Sou do morro, sou favela, mas meu coração se apaixonou.
To begin, let's define exactly what we mean when we talk about renewable power. Renewable energy is simply energy derived from natural resources that naturally replenish themselves at a rate equal to or faster than they are consumed. A prime example of this is solar energy, which is the radiant light and heat from the sun that we harness using a range of ever-evolving technologies. This brings us to the crucial question, why is solar energy so important in modern society? There are three major reasons. First, it provides energy security and independence. By generating power locally from sunlight, countries can drastically reduce their vulnerability to global fossil fuel, supply chain shock, and also price volatility. Second, it drives economic vitality and job creation, transforming the solar sector into a massive economic engine that has created millions of jobs worldwide across manufacturing, installation, engineering, and also maintenance. Number 3, we have seen a massive decline in the levelized cost of energy, or we call it as LCOE, thanks to manufacturing overcapacity and technological advance. Solar PV has officially become the cheapest sources of new power generation in history for most parts of the world. Now, let's take a look at the global use of solar energy, which is currently shaped by three major trends. First, we are witnessing rapid market growth. Solar photovoltaic technology has expanded so massively that it now generates over 8% of the world's total electricity supply, remarkable single-handedly meeting roughly 75% of all new global power demand growth in recent years. Number 2, there are advanced technology shifts occurring right now. Large-scale solar farms are rapidly upgrading to bifacial panels, which absorb light from both sides and integrating battery energy storage system, or we call it as a BESS, to save excess daytime power for nighttime use. Number 3, there is a widespread regional adoption, with major markets like the United States, India, Europe, and also the Middle East leading to the charge with highly robust annual installation rates driven by aggressive climate targets. Malaysian use of solar energy thrives on an ideal geographic advantages, receiving 4 to 5 hours of peak daily sunshine near the equator. This supports the nation's aggressive capacity targets, with installed solar capacity already crossing 5.7 gigawatts towards a 17% renewable energy target by 2050 under the National Energy Transition Roadmap. To fulfill this, innovative corporate green energy access program like CRIS allow private business, especially expanding data center hubs in Johor and Selangor, to buy electricity directly from developers, driving immense corporate investment back into the local grid.
Next, let's talk about the scientific principles behind solar panels. So the first one is the science behind solar energy. Solar energy is a product of the sun's nuclear fusion process, which releases photons into space. The photons then travel to Earth, where solar panels, which consist of photovoltaic cells or PV cells, intersect them. As the photons strike the PV cell surface, they excite the electrons in the semiconductor material. The photovoltaic effect. Photons strike a PV cell, they will reflect off the cell, pass through the cell, or be absorbed by the semiconductor material. Only the photons that are absorbed provide energy to generate electricity. Electrons are dislodged from the material's atoms. The flow of electricity in a solar cell. The movement of electrons toward the front surface of the PV cell creates an imbalance of electrical charge. Electrical conductors on the PV cell absorb the electrons. The conductors are connected in an electrical circuit to an external load, such as a battery. Electricity flows through the circuit. This diagram explains the inside of a photovoltaic cell, where the photovoltaic effect happens.
Let's explore how solar panels are categorized by their materials. First, monocrystalline. Monocrystalline panels are made from a single pure silicon crystal offering a high efficiency and a sleek dark look at a premium cost. Second, polycrystalline. Polycrystalline panels make multiple silicon fragments together, providing a budget-friendly option with moderate efficiency and a distant bluting. Finally, thin film technology. Thin film technology deposits a photovoltaic layer onto flexible substrate like glass, plastic, or metal. To lower in space efficiency, they are uniquely lightweight and flexible for specialized installation. Next, let's look at the critical component that keeps solar energy setups operating safely, the charge controller. Its primary job is to regulate the voltage and current coming from the solar panels to ensure connected batteries are charged safely and optimally. Without a charge controller, solar panels would continue pumping high voltage electricity into a fully charged battery, leading to dangerous consequences like overheating, electrolyte, or catastrophic thermal runaway in lithium batteries. To prevent this, the controller continuously monitors battery voltage, dropping the incoming current to cutting it off entirely once maximum capacity is reached. This constant protection is what makes a larger battery storage system viable and long-lasting. In modern systems, this battery bank serves two major purposes. Number one, time shifting, which involves storing excess electricity generated during peak sunlight hours at noon to be used later during high-demand evening and night hours. Number two, load shaving, which helps the commercial user draw from the battery during peak rate periods to avoid high-demand charges from utility companies. Depending on the needs of the project, three main types of battery are typically used to achieve this, which is lithium iron phosphate, LFP, lithium nickel manganese cobalt, NMC, or traditional lead acid deep cycle variants like AGM and gel units. Now, let's talk about the inverter. While our panels generate electricity, they produce direct current or DC power. However, our household appliances require alternating current or AC power. The inverter steps in to convert low or high voltage DC from panels and batteries by using rapid electronic switching transistor to shape a stable oscillating pure sine wave AC. This process is absolutely essential because it ensures the generated power is indistinguishable from or even cleaner than standard utility grade power, allowing our appliances to run safely and efficiently.
Let's take a look at the scientific instrumentation and measurement in solar panels. The first one we have voltmeter. Voltmeter function to check open circuit voltage or VOC of solar panels. Verifying the string voltage before the inverter connection. Testing battery voltage. Ensuring the inverter AC output is within the range and detecting the voltage drops. Next, we have ammeter. Ammeter function to check short circuit current of solar panels, measuring charge current in batteries, testing inverter output current, detecting overload conditions, and identifying imbalance in three-phase systems. Next, we have the solar irradiance meter. So, solar irradiance is generally measured in watts per square. This unit of measurement allows for a clear understanding of how much solar power is being received per square meter of a given surface area. The higher the irradiance level, the more solar power available to be converted into electricity. Next, we have clamp meter. Clamp meter functions to measuring current in live circuits, checking inverter AC output current, measuring load current without shutting down the system, diagnosing imbalance in three-phase systems, and ensuring safe and quick testing.
So let's look at how a solar energy system actually works. Firstly, it all starts when sunlight hits the solar panels. Through photovoltaic conversion, the panels absorb this light and turn it into DC, which is direct current power. However, most of our home appliances run on AC, which is alternating current. That's why the inverter comes in. It converts that raw DC power into standard AC power so it is safe to use. And once converted, the electricity passes through a utility meter which tracks exactly how much the solar energy is being produced. Finally, this clean energy will flow into the public utility grid, distributing power to the local network and sharing the benefits with the community. Next, let's talk about the real-world applications. So where do we see this technology in action? First, in residential solar systems, where rooftop panels help homeowners lower their monthly electricity bills. Next, commercial buildings, such as malls and factories, use them to cut down on heavy daytime operational costs. And going beyond Earth, satellites and space rely on solar arrays as their primary and highly reliable power source. For a local example, which is Malaysia, Malaysia is heavily investing in large-scale solar, which is LSS, initiatives led by the Energy Commission. Mega projects like LSS Petra generate massive amounts of clean electricity at a very lower cost. This power is fed directly into the TNB national grid, playing a huge role in supporting Malaysia's net zero carbon goals.
We know that solar energy not only offers their benefits, but actually has several challenges. Before we discuss about their challenges, let's take a look first at solar energy benefits. Firstly, renewable and sustainable. Solar energy is a renewable source that will not run out because it is continuously supplied by the sun. Secondly, low maintenance costs. Solar panel require minimal maintenance and low operating costs since it is no moving part that carry out over time and can last around 25 years, providing long-term saving. Another benefit of solar energy is environmentally friendly because it produces little to no carbon emission and has minimal environmental impact on the surrounding and living organisms. That's why solar energy can be described as a clean energy source. In addition, solar energy can reduce electricity bills because it can reduce relying on grid electricity and lower electricity costs. Using of solar energy, no need to install complete solar system since solar light can be powered directly by sunlight. Solar energy can be used as energy storage and backup power. Solar energy can be stored in battery and using it during peak hour or when there is no sunlight. It can be also using during power outages as backup electricity. This benefit makes solar energy an attractive and sustainable alternative to conventional energy sources. Let's go through the challenges and limitations of solar energy. Firstly, weather dependence. Solar energy works based on sunlight, so it becomes unstable during weather change and cannot generate electricity at night. It requires backups like battery, which it will increase the cost of living for solar energy user. 3 is energy storage limitation. Limited energy storage means solar system cannot fully meet energy demand. Solar systems are less efficient due to lithium batteries that degrade easily and depend on limited raw material. So because of that, energy will lose during the storage process. High initial installation costs. Solar system require high upfront installation costs due to the additional equipment and maintenance. Also, the return on investment usually takes several years. Large land requirement. To build a solar energy, they require large area of land to generate electricity efficiently. Suitable land and infrastructure are important for installation and operation of the solar energy.
Now, let's move to the future development and innovation. The future of solar energy is not just about making panels, it is about making them smarter, more efficient and capable of providing power even when the sun goes down. Here are the 3 major innovations driving the next generation of solar energy. The first one is bifacial solar panels. Imagine a solar panel that works twice as hard. Bifacial panels don't just soak up direct sunlight, they also catch the light reflecting off the ground beneath them, squeezing every last drop of energy out of the day. The second one is solar tracking technology. Just like a sunflower tilts to follow the sun from dawn until dusk, solar tracking technology ensures our solar panels are always facing the sun at the perfect angle to maximizing energy production from morning to night. Last but not least is the improved battery technology. Solar power is amazing, but what happens when the sun goes down? That is where revolutionary battery tech comes in. With longer lasting, safer, and massive storage capabilities, the future grid will run smoothly and on daytime sunshine, even in the middle of the night. To wrap things up, we have seen how solar panels utilize the photovoltaic effect to instantly turn sunlight into clean DC power, which is then inverted for our daily use. But capturing energy is not enough. We need precise instrumentation. advanced monitoring systems act as the brain, tracking data and detecting faults early to keep our solar system operating at peak performance. Looking ahead, solar energy is no longer just an alternative. It is the foundation of sustainable development. With rapid innovation in battery, storage, and smart tracking, solar will lead the charge towards a cleaner, zero-carbon future.